All right. Thank you everyone for attending. This is the senior design review for the NASA Lunabotics EE team. Just to give you a brief outline of the presentation, I'm going to go over who our team members are, a brief overview of the competition, our evidence of our system redesign, our optimizations we went through, our actual design, our test results, and then I'll just finish by giving a little overall progress and what the next steps will be until our final design is due next week. And also here's a picture of the Lunabot just to give you an idea of what it looks like. So we have two buckets. Our motors are sitting back there. All our electronics and stuff is actually behind this bucket back here. So the team overview is myself, Matthew Yonker, Dave Wazinski, Anthony Wong, and our advisor is Dr. John Helferty. So a little overview of the NASA Lunabotics competition. So there is a point system involved for our robot. Here's a quick breakdown. Some of the things to point out are 1,000 points for passing inspections. A good amount of the points is from the amount of regolith we mine. So the point of the robot is really to mine the regolith and deposit it into a bin for points. How much bandwidth we're using, the mass of the Lunabot, and energy consumed, dust tolerant design, and full autonomy, which will add up to a total point. So just to give you an idea of what the Luna Arena looks like, this is where the Lunabot will be competing in. There's a start position with 4 unique positions where the robot will be placed in facing a random direction. There's an obstacle arena with rocks and craters. That's what the robot needs to navigate through. And then there's a mining area. When you're done mining, you return back to the starting position and you dump your soil. So now I'm going to talk about our system redesign, some of the changes we went through. So this was our initial Lunabot prototype all the way back in senior design 1. It was really just so we could understand, how the treads work, give us an idea of how we were going to use the Arduinos to control the motors. So our old system overview, it pretty much has all the main components that we still have with our final design. You can see some things such as the laptop, the Kinect, shunt, battery, Arduinos that go to speed controllers and motors. That's still all in our final design. So here you can still see the laptop, we have the Kinect, here's our sensors and motor control system, we have our compass. Now onto our power system. So this is how we originally laid out our power. A couple of interesting things to point out is we at one point had an emergency backup battery. I'll go over why that was changed. And you can still see a lot of the components from the old power system are still existent in our new one, such as the shunt. We have an emergency switch, a fuse box, and the PC is also powering some things in our old diagram. As you can see, the revised, here the green is being powered by the battery. This bottom section is being powered by the laptop. And you can still see a lot of the same components still exist. We have our battery, our shunt, relay, fuse box, and the laptop is powering these Arduinos. The Arduino is powering the compass. So our old power budget, this is what we got from looking at data sheets and seeing what is the maximum current we could be drawing from the motors, Kinect, actuators, and fans that we had to cool our motor controllers. And you can see we were sitting at almost 80 amps of current from the battery. Our revised power budget, the Kinect is still the same, but our motors really went down, and that's because the motors, it's just not driving at the full speed that these motors could possibly go. So that really came down a lot. And so our current draw really went down a lot, and that's why we could remove the battery that we had in our old system design. We didn't need that extra possible current, especially considering that the battery can provide a maximum amperage of 90 amps. We were really safe with this, so we didn't need the extra battery. For our old autonomous system, this was just the initial concept we had of certain states that we would need: starting, orientation, navigation, digging, returning, and dumping, stopping after 10 minutes. So then when we went to actually code the autonomous system, this is how it was coded. So you can see we have an initialization, checking our orientation. We have turning to orient ourselves at the start. We have moving, digging, avoiding obstacles. And you can see our most current autonomous system. There's a couple more states. For instance, you can see The moving forward is now actually in 2 separate states. That was just to make the logic a little bit simpler to program. And also the digging the dig is still there, and the moving to the bin was a little fleshed out where there's a couple more states here. So the design of our Lunabot. I'm just going to go over the 4 main systems, which is power, motor controls, power monitoring system, and our autonomous system. So first, the power system. You can see here are the wires coming from the battery, which goes into our shunt. That goes into the relay. Here's our emergency stop button, fuse box, and the fuse box connects to the motor controllers. Some important things to point out is that the emergency switch is in series with the relay. Power is delivered to the subsystems through our fuse box, and each fuse is rated for 10 amps. And we also have a voltage regulator, which you can't see here, but it's coming from the fuse box. And our voltage regulator delivers 12 volts to the Microsoft Kinect. Our motor control system, so we have 2 motor controllers, and each one of them is getting a signal from this Arduino here. Each controller powers 1 motor and a pair of linear actuators. So we have 2 buckets, we have 2 pairs of linear actuators. So this controller controls 1 motor and 2 linear actuators, and this one controls another motor and another 2 linear actuators. Like I said, power is regulated through, the motor controllers we use is the Sabertooth 225 motor controllers. The 2 is for 2 channels, 25 is for 25 amps. And the downside of this configuration is that the linear actuators can't be individually controlled. So on here we have 1 motor, 2 linear actuators. Both of those linear actuators have to move at the same time. We can't individually control them. For our power monitoring system, we are using a 10 milliohm shunt. It has a linear response over a large range, but the error grows as the voltage drops across the shunt. And the wires from this shunt are shielded, as you can see right here, to reduce the noise in this system. So for our time system, to give you a little overview of how the design actually works. So first when we hit the go button, it'll initialize. So this is where we start our motor controls, our linear actuator controls, and we're checking, and we turn on the compass. So with these turned on, it'll check the compass and orient itself to face the dig site right at the start. That's when the Microsoft Kinect, which is our vision system, will be turned on because it'll be facing the open arena, and there's no chance of it facing a wall at the start. After the Kinect is starting and it's facing the dig site, it'll start to move to the dig site. If an obstacle is detected, it'll turn. There's some logic in this turn block to actually control, if it's turning left or right. After that, it'll go back when no obstacle is further detected after turning. It'll keep moving back to the dig. Once the dig site is reached, it'll start digging. Return to check compass. Now it'll be trying to dump, so it'll go turn to dump, come back to check compass, keep going between these 2. Once it's facing the dump site, it'll start moving to the dump, continuing to avoid obstacles. When it reaches the start position, it needs to orient itself so it's in front of the bin. So if the bin's over here, the robot's over here, it needs to come and be in front of the bin to dump our soil. So we have our move to bin. When it reaches the bin, it's right in front. Our bucket will come up and dump our soil in. And then we also have a block to check the dump status and go back. And then if there's still more time permitting, we'll go again. And we have a timer here. When 10 minutes is reached, it'll stop it by just a Java command system .exit. Our test results. So our power system was tested with motor control system to ensure that everything in our entire robot can be powered. Each line coming from the fuse box at this test was delivering 28.6 volts. And 28.6 volts was below the maximum voltage rating for the motors, which is 30, so we were good there. So here's a test we did with our motor controls. So our robot can move forward, backward, left, and right. And because each motor is on a separate channel, we can control each motor individually. So as you can see, turns forward, backward, left, right. And at this time, this was using a manual control wirelessly. Commands are sent to the laptop. Test results for our power monitoring system. So here is a graph of amperage over time. And here is our watts over time. So this is the robot starting up and it's just idle waiting. And then this is switching the motors off and on. And then this here where it's kind of spiky right here, but it's not shooting up, this is us trying to drive the robot slow. So not full throttle, we're kind of trying to move it slowly forward. Data received from the shunt, if the Arduino receiver is stored in RAM, and then it's written to a text file after the power monitoring, after the robot's run is completed. The data was stored in RAM and written to a file because the RAM access time is much faster than the hard drive access time. So writing to RAM ensures that we won't have any access speeds time when we're trying to write to this file constantly. And a typical 10-minute run generates a file size of 50 megabytes. So this is a big text file, but this is how we knew we wouldn't have any problems with RAM overflowing because 50 megabytes is very small. The size of our RAM is 8 gigabytes. So we would have no problem with overflowing the RAM there. And for our autonomous system, let me play this video. So this is testing. Here you'll see a test. You'll be able to see our vision system detecting the object. And then down here, there's code printing out, which is actually here. I'll go over that in a minute. But as you can see, the robot's coming up to an object. You can see it here. There's a little bit of chatter before it fully stays completely red. And then as you see, as it's backing up, the object is fading out. And there's a little bit of chatter before it turns off and it's not detecting the object anymore. Here's our state machine. So this is code that was written to debug the state machine, so we could tell what state we were currently in the code. As you can see, the state machine begins by initializing. It checks the compass. Once we're facing the correct direction, the Connect will initialize. It'll print out a value of the average distance that it's reading. It'll keep doing this. It'll say it's trying to move forward. It'll keep, this is the Connect class again. It's running in a separate thread. And it'll print out the value. Eventually, so our initial value is 1442. When the value from the Connect goes below that, that's an obstacle detection. So 1435 is below this 1432. It'll go to turn decision, and then it'll start turning until the object is no longer in front of the Connect. And here is just a little test result we did, just to detect the minimum size we could detect with our vision system. This ball is 15 centimeters in diameter, which is smaller than the minimum size object that we could have in the competition, which is 20 centimeters in diameter. So we just wanted to make sure to run this test that we would have no problem in the competition. Any questions?
Actually, I have one question.
Yeah.
Going back to your test, I think it was your test slide. You reported that you were getting 28 volts from out of the fuse box. Correct me if I'm wrong, but like before, earlier on your slide, I think you're supposed to get 25 volts. See what I'm talking about?
Yeah. Actually, it's a pretty good question. Okay, so the voltage from the battery, coming out of the battery, when it's fully charged, it's a little bit higher. And then mostly our operating voltage for most of the time is 25.9 volts. But when the battery's fully charged, we could see a maximum of 29 volts coming out the battery. And then as it's almost completely discharged, there's a very quick drop off here. So that's the voltage response from our battery. This is 100% charged right here. So that's why that is. This was being tested when the battery was completely charged. Any other questions?
You mentioned this 10 milliohm power shunt, and then there was a comment there about exponential error increases. What's going on? It's just a resistor, is it not?
Yeah. The thing is about the shunt. So the voltage across the shunt is it's very small.
This slide where it says.
Right here?
That's it.
Yeah. So.
Error grows exponentially as the voltage drops and plus the shunt decreases.
And that's because, first of all, as so we're using an amplifier to amplify the voltage coming off the shunt, and that amplified signal is then sent to the analog to digital converter on the Arduino. when the voltage goes down across the shunt,
No, it's not the shunt causing the problem, it's the data acquisition system. Because the resolution of the ADC is fixed, and therefore there's a problem. I don't think it's exponential.
It's 10 bit.
it's because
10 bit, 8 bit.
the amplifiers produce a lot of
Well, I was
distortion
concerned that you're
close
giving
to
the
the.
impression there's something wrong with the 10 milliohm shunt, but that's just a
No.
resistor.
Yeah, there's nothing wrong with the shunt. It's really the amplifier close to the voltage rail will produce a lot of distortion. So just to
No, no,
get
that part I know, but it's just kind of confusing, I think, to specify it that way.
yeah, and I mean you can actually see in our test results here. So right here, this is nearly zero. That's
It's awfully strange too that the amperage actually clamps like that and then oscillates back and forth when the motors are moving.
what do you mean like that?
Yeah.
No, that's us switching the motors. That's us going forward, going forward.
I mean, but the
going forward.
level stays the same except for a little oscillation. Maybe that's what the motors do.
Yeah, this is error right here. This is some of that is error coming from the amplifier.